Hello and welcome to the second video review for the Algebra 2 Common Core Regents exam. Today's video is going to be focusing on Unit 2, Functions as the Cornerstones of Algebra. In this video, here's how it's going to be laid out. Okay, we'll first look at a reminder of all the things that were taught in this particular unit, all the particular lessons we learned. Then I'll take a brief moment to look at the three Common Core standards associated with this unit. Take a time just to talk about some brief, very important terminology. Then we're going to look at some topical reviews before summing up the most important things you should be able to do from this unit. Okay, as we go along, just remember, feel free to pause the video. You can come back to it. You can the next day, because where you left off is where the video will start up again. Okay, but hopefully you're creating a study guide as well. Okay, so here are the lessons that we learned in this unit, in Unit 2. There were 7 lessons. Okay, and the first 5 lessons were really introductory material that were crucial for later units as well as this unit. Okay, it's setting up functions in general. And as you have seen so far, functions are a big part of this course. Here are the Common Core standards associated with this unit. We have finding an inverse function. Okay, we've done that plenty of times this year. And also sketching graphs and showing key features given either a verbal description, an equation, a table of values, okay? And we're looking at key features such as what are the intercepts of the graph, x and y intercepts, where is it increasing, decreasing, positive or negative, relative maximums and minimums, any kind of symmetries that occur, and behavior. And periodicity we will be looking at with the trig stuff. And as you can see, these deal with a lot of different types of functions: polynomial, exponential, logarithmic, trigonometric functions. And we looked at all those things within future units. Okay, but this unit was really just a setup about the general things about functions. Okay, and the last standard is looking at 2 different functions and comparing them. Maybe given one algebraically and one numerically in tables, or one by verbal description, one by graphically, or any combination of those, and be able to compare the features of them. Okay. Those are the things that the Common Core exam is going to be assessing you on. Some very important basic terminology with this unit, since this unit is about functions and the introduction to functions. The term function is a very important term to know. A function is defined as any kind of a rule, and meaning it could be an equation, it could be a graph, it could be a table of values, it could just be a list of points. Any kind of rule that assigns exactly one output or one y value for each input value. So essentially, if you had inputs and you had outputs, the only way you can have a function is if each input goes to one and only one output. So like this would be an example of a function. It doesn't mean it can't go to the same output. It can go to the same output, but each input has only one output. And that's the definition of a function. You punch something into the function, you only get one thing out. You can't get 2 things out. And with graphs and functions in general, you have 2 terms, domain and range, that occur a lot. Domain are all the possible input values, usually the x values in equations, and range are all the possible y values, all the output values. So let's take a moment just to note the different types of notations for domain and range. Okay. For a lot of functions, you can put any value that you want in, and you can get any value out. So when that happens, you have all real numbers, and that's notated by a fancy capital R. For anything else, if there's certain x values that will work or won't work, or only an interval of values that will work, there's these three notations that we can use. Okay. Set builder notation can be used for domain or range. Okay. So it's going to be, if it's domain, it's going to be x, and this can be written as x such that, and then you write the condition. So for instance, if only the values greater than or equal to 9 work as inputs, then that would be your set builder notation. You could also have it for the range as well, so all values of y such that maybe -3 is less than y is less than 9. Okay, that would be an example of set builder notation. Inequalities is very similar, except you just don't have the sets. So you just have things like x is greater than or equal to 3, or y can't be 7. You know, any kind of inequality. And interval notation, that's where you have the parentheses and the brackets. So if it's between 3 and 8, but not including those values, you would say something like 3 to 8. In inequality notation, that's equivalent to 3 is less than x is less than 8. You could have brackets, so if we had bracket 3 then to 8, that's the same thing in inequality notation as 3 is less than or equal to x is less than 8. Okay, so the brackets mean equal to, and the parentheses mean not equal to. Okay, now if you're dealing with inequalities such as x is greater than 7, that goes all the way up to infinity, then you're going to have 7, your lower value, up to infinity. Anytime you're dealing with infinity, it's always a bracket. Always a bracket. So here's the set builder notation. Here's just the inequality notation. And here are the interval notations. To identify a function, there are certain things you can do. Graphically, you can use the vertical line test. So if you have a graph such as here, and you have a function that looks like this, if you can draw vertical lines, and it only passes the function at one point, say here, 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 and so forth, then you know that's a function. The vertical line test, what you really want to do is you want to look for one line that's a vertical line that goes through twice to determine if it's a function or not. Okay, if you can find one line that goes through the graph of a function, say we had this graph right here, all you need is just one line. So this is the line I'm going to draw to show that it goes through twice. And what that's really saying is that this x value right here has two different y values associated with it. Okay, so it fails the definition of a function. Because for a function to be a function, every input has to have only one output. And the vertical line test, if it passes through more than once, indicates more than one output. In a table of values, say we had a table of values, it could be sideways or up and down, like in your calculator or like this. If you have two x values in here that go to two different values, so say this one goes to 0, this one goes to 5, the same x value to two different values is the same thing as failing the vertical line test if you were to graph those points. Okay, that's what you're looking for to see if it's a function or not. So this is not a function. Okay, this one up here is a function, not a function. For the equations, almost all the types of functions we've looked at this year, rational, polynomial, radical, quadratic, cubic, those are all functions. The way you're going to tell if it's a function or not is you're going to look at the y in the equation. So if you have something like y equals x squared minus 5x plus 2, it's quadratic or polynomial depending on how you look at it. This is a function. Any equation that has an even exponent on a y. So even exponent on the y. Or if you have an absolute value on the y. Those are the cases where it's not a function. Just by looking at the equation. Okay, and the reason for that is because if an even exponent on y, say you have something like y squared is equal to 5x plus 2, well, you can plug in a positive and a negative value for y. You have two different outputs for the same possible input. That's why that is not a function. If you had absolute value of y is equal to 7x plus 3. Again, plug in positive or negative, you get the same results because the absolute value makes things positive. So that is not a function. Alright, so that's just a word about identifying functions. Vertical line test. Draw a vertical line to see if it's a function or not. If it passes through more than once, it is not a function. Looking at the table, if x value goes to two different y's, it's not a function. And then examining the equations, if there's an even exponent on the y or an absolute value on the y, they're not a function. Okay, another thing we dealt with was proper function notation. Now in equations you can have things written as y equals something. Okay, and that can still be a function. Y equals 3x plus 2 is considered a linear function. But when you're talking about using things with proper function notation, that's where you're going to use the f of x notation. This is proper function notation. Okay. The f, or it could be g, could be an h, could be anything, could be an a of x, could be a c of x. Maybe if you're talking about the volume in terms of a function of x, it could be v of x. Okay. This letter out front is the name of the function. And inside the parentheses is going to be your input variable. Okay, that's just the notation. Okay. And of course, you only use function notation if you have a function. Now, evaluating functions. Okay, so if I have f of x is equal to x squared plus 3x minus 7. If I see something like f of 2, that's asking me to evaluate the function at 2. Whenever you evaluate values, make sure you put parentheses around what you're plugging in. Okay? Because if you have something like f of negative 5, you want to make sure you put that negative 5 in parentheses before you square things, or raise them to the third power, or do whatever it says to do. So f of 2 is going to be parentheses 2 squared plus 3 times parentheses 2 minus 7. Okay. That gives me 4, and 6 is 10, minus 7, so that gives me 3. If I evaluate negative 5, it's negative 5 in parentheses squared, plus 3 times negative 5, minus 7. So it's positive 25, minus 15, minus 7, which gives me, hey, look at that, 3. I did not intend that to happen, but hey, happy coincidence. Now remember, just because it ended up with the same output does not mean that the original thing was not a function. Okay. What that just means is that two different outputs ended up with the same, two different inputs ended up with the same output, and that's perfectly allowable, just as long as an input does not go to two different things. Yeah. Alright, now let's look at function composition. This occurs when you are evaluating a function at a function. Okay, there's a couple of notations for function composition. One is the fog notation, f of g of x. The other notation is f of g of x. Okay, it looks like you're kind of evaluating f at the function g of x. these two are equivalent and mean exactly the same thing. It's just different notation. Now, of course, if the functions are h and k, you could have something like h of k of x, and you can have h of k of x. Okay. Now, a function notation, order is important. What this little symbol really means it's composed of. You're composed of k. H is composed of k, which means you have to do k first. Likewise, h of k of x, you have to work inwards, outwards. So k is going to be evaluated first. So if I say f of x is 3x plus 2, and I say g of x is 1/2 x minus 3, and I want to know what is f of g of 4. Okay. What I'm going to do is I'm going to work inwards, outwards, and I'm going to evaluate g of 4 first. G of 4, let me just do this down here, g of 4 is going to be plugging in 4 for g. So 1/2 of 4 minus 3, that's 2 minus 3, which is -1. So f of g of 4 is really the same as f of -1, because g of 4 is -1, which gives me 3 times -1 plus 2 equals -1. Oh, look at that, another happy coincidence. We ended up getting the exact same thing. Okay. Will that always happen? No. And just take a note, if I were to go the other way, if I said g of f of 4, I would have to evaluate f at 4 first. So f of 4 is 3 times 4 plus 2, which is 14. So this is really g of 14. Oops, let me rewrite that again. G of 14, which is 1/2 of 14 minus 3, which is 4. Okay. Now note, you could also do evaluation using the fog notation, but it's exactly the same thing because they're equivalents. Okay. All right, now a word about one-to-one functions. So one-to-one, the formal definition is that if you have different outputs, it implies you're always going to have different inputs always imply different outputs. Okay. So if I plug in 3 and I plug in 5, x equals 3 and x equals 5, it's implied with the one-to-one function that my output is not going to be the same thing. Okay, that'll never happen. So the way we test to see if something is one-to-one or not is by applying something called the horizontal line test. Okay, the vertical line test will tell you if it's a function or not. In this case, there's no place I can draw a vertical line that intersects more than once. But the horizontal line test is what you're going to use to see if it's a one-to-one function. Okay, this one is in fact a one-to-one because I can't find anywhere where it intersects more than once. Okay. Inverse functions, so we'll saw that a little bit in Unit 1. But since we introduced one-to-one, that's an important thing to note because in order for an inverse, so notice every function has an inverse. The question here is whether or not that inverse is a function itself. And the only way that the inverse can be a function is if the original function was one-to-one. Okay. And the way you find an inverse is by just switching the x and the y variables and then solving for y. So the x and y switch. So if you had something like y equals 3x plus 2, and I ask you to find the inverse, what I'm going to do is I'm going to switch the x and the y to write x is equal to 3y plus 2. Okay, and then you just solve for y, subtract 2 from both sides. So y is equal to x minus 2 over 3. Okay. Now that's the inverse of the line, the linear function y equals 3x plus 2. Now if I were to use proper function notation, say I started off with f of x is equal to 3x plus 2. The proper inverse notation is going to be f to the negative 1 of x is equal to x minus 2 over 3. Okay. This negative 1 is just the inverse function notation. Don't get this mixed up with if you have 3 to the negative 1 is equivalent to 1/3, because one of the properties of exponents, negative exponents, go on the bottom. That's not what's happening with the inverse function notation. Okay, this is just a little notation saying inverse. Okay. Now, because the x and y values switch to find the inverse, that means the domain of a function becomes the range of the inverse. Okay. Likewise, the range of a function will become the domain of the inverse. And that should make a little sense, because if you're switching the x and the y, then all the domain values, which are the x values, become the y values in the inverse, become the range. All the y values in the function will become the x values in the inverse, that becomes the domain. And the last thing about inverses is that if you look at them graphically, okay, because the x and the y switch, it's really just a reflection to that y equals x line. Okay, so a function that looks like this will reflect to become something like that. Alright, and then let's look at some key features of functions and their graphs. So if you had a function, let's say I have some kind of polynomial function that looks like this. Okay. There, let's say it goes through the x-axis at -7, it goes through the x-axis at -2, maybe the y-axis at -14, and to the x-axis again at 4. Okay. The x-intercepts are just wherever the function has a y value of 0. Okay. To find out the x-intercepts, what you're going to do is you're going to set whatever the function is equal to 0 and solve for x. Okay, that's what you're going to do to find the x-intercepts. And that just occurs wherever the graph intercepts the x-axis. Let's label this the x-axis, this is the y-axis. The y-intercepts occur wherever the function has outputs, it has an output, should I say, for x equals 0. Okay. Wherever the function has an output for x equals 0. So we're going to plug in x equals 0 and solve for y. Now notice that there's only going to be one y-intercept, but there could be multiple x-intercepts. And that's because the y-axis, if you were to have multiple y-intercepts, like say here, here, and here, that would fail the vertical line test. It wouldn't be a function. Okay, so there's only one y-intercept. for a function. Alright, and zeros and roots are really the same thing as the x-intercepts. Alright, so there's some key features of graphs. Now let's look at some more key features. Maximum, minimum, increasing, and decreasing. Okay, let's kind of use the same values we had before. -7, -2, -14, and what was it, 4. Okay. The maximum points are where it changes from increasing to decreasing. The minimum points are where the graph changes from decreasing to increasing. Okay. And increasing occurs, and you're always moving in the positive x direction when you're looking at these things. Always moving in the positive x direction. Increasing occurs when the x values increase, the y values increase. So as the x values increase, the y values increase. Decreasing occurs when the x values increase, always move in the positive direction. The y values decrease. So let's say I have in this graph a maximum. Notice it changes from increasing to decreasing roughly about here. Let's say we have a maximum located at -3, 8, and we have a minimum located at maybe 1, -20. Okay. So for this particular graph, I would say that the max is at -3, 8. The minimum value is at 1, -20. It's increasing over a certain interval. Okay, now it's where it's increasing. It could be multiple places. And in this case, it looks like it's increasing below -3 as an output. So it's increasing x less than -3. And it's also increasing x is greater than 1. Okay. Notice I'm labeling these with the x values, not the y values. The y values determine if it's increasing or decreasing, but the x values are where they're increasing and decreasing. Okay. And decreasing between -3 and 1. So -3 less than x less than 1. Okay. Notice I did not include those values for increasing or decreasing because technically at those points, at the maximum and at the minimum, it's neither increasing nor decreasing, it just is. Okay. We refer to those points as max and min, not as increasing or decreasing. Okay. But up to that point, it increased to -3, 8, and then it began to decrease all the way down to 1, -20, and then it increased after that point. Okay. But at those particular points, it's neither increasing nor decreasing. Now another thing I want to point out is this particular graph only had one max and one min, but you could have several max and min, and in those cases you could be referred to as relative maximums and relative minimums. Okay. in an absolute max and an absolute min, that occurs when there's absolutely no values below as an output of the minimum. That's going to be an absolute minimum. And no values above a maximum point would be an absolute maximum. Okay, and one more slide for key features. You might see notations like this. F of x is greater than 0, f of x is less than 0, f of x equals 0. What those are essentially meaning is if it's greater than 0, then that means that your outputs are positive. Because all the numbers that are greater than 0 are positive numbers. So you're looking for all the x values where it is positive as an output. Or in other words, above the x-axis. Okay, all the x values that provide outputs above the x-axis. Less than 0, outputs are negative. You can think about that as below the x-axis. Okay. And equal to 0, the outputs are 0. Okay. And you can think about that as on the x-axis. Now we saw a term for that, zeros, roots, x-intercepts. Those are all terms that refer to f of x equals 0. Now, of course, you could have things like f of x is greater than or equal to 0. In that case, you would include the values on the x-axis. Okay. Likewise, f of x is less than or equal to 0. Okay. So if I had this function, let's use the same function again. Goes through -7, -2, -14 on the y, and +4. So if I said, where is this function greater than 0? You're looking to see where it is above the x-axis. Here it's above, there it's above. Okay. So greater than 0 would be -7 less than x less than -2, or x is greater than 4. Okay. Now let's look at where it says f of x is greater than or equal to 0. That would be -7 is less than or equal to x less than or equal to -2, or x is greater than or equal to 4. Okay. So notice there's an equal to there, you can include equal signs. If there's no equal to there, you don't include equal signs. Okay, now let's see what happens if it said less than 0. Okay. In that case, I'm going to be looking at where the graph is below the x-axis. So here and here. Okay. So it's less than 0, where x is less than -7, or -2 is less than x is less than 4. Okay. By the way, a little note about inequalities, especially compound inequalities. You will never have greater than symbols with compound inequalities, like for instance 3 greater than x greater than -1. You'll never have that. Okay. Even though that's sort of a true statement, what you always do is you always label the smallest number first to the larger number. Okay, so often I see students who write -1 is greater than x greater than 3. Okay, and that is wrong, because if you look at that in general, is -1 greater than 3? No. Okay, that's a false statement. So just be careful about that with the conjunction notation. Alright, so here's a summary of the most important information. So from this unit, you should be able to do several things. Okay. First, you should be able to determine whether or not something is a function or not. Vertical line test, look at the table, look at the equation. Okay. You should be able to determine if something is function is one-to-one. And you're going to be looking at the horizontal line test to see if that's going to be one-to-one. You should be able to use proper function notation, the f of x, g of x, and so forth, to state the equation of a function, its inverse, or the composition of functions. You should be able to evaluate functions and compositions of functions, just remembering that, being careful to add parentheses where they're supposed to be added. You should be able to find the equation of an inverse by just switching the x and the y. You should be able to look at a function, either the equation, the graph, or its table to determine the domain and range of it, or the domain and range of its inverse. And remember, the inverse, domain and range are flipped. Okay, so the domain of the original function becomes the range of the inverse. The range of the original function becomes the domain of the inverse. And you should be able to look at a graph and identify key features such as where the x-intercepts are, the y-intercept, notice, not plural because there's only one y-intercept, zeros, roots, maximums, minimums. Okay, you should be able to figure those out from either the graph or the equation. From the equation, you can always graph it to find out what it looks like. Okay, but you should be able to look at the table of values at least to find those values. Okay, and also find out where it's positive, negative, or zero. Alright, thank you for watching. Hopefully this has been a good review for you. Thank you for being patient with my messy handwriting. I'm still working with how to make these videos look nice because I'm using the pinch function on my iPad. But sometimes if I'm zooming in and out, I make stray marks. So thank you for being patient with me. Hope you enjoyed it, and I'll be making Unit 3 videos soon. Thanks.